reply that you want.
Hi, so welcome to this live session at BYJU'S, and I am going to discuss about electrostatics. Now, this is a chapter which you encounter in the beginning of your 12th standard, right? And see, apart from the basic properties of charges, which were like extremely simple, you know, this chapter is nothing. This has just a few application of the things which you have learned in mechanics, and that's what you keep on learning. See, you learn about electric field. That's a new word. But you know that's actually not a very difficult idea, right? It's a very simple idea. Similarly, from potential energy, you learned about potential, something you've already learned in gravitation and all that. So this chapter, although it is really huge, that of course you must have noticed that it is almost of the length of a couple of mechanics chapters, and it's pretty easy also, and scoring, because in JEE it has a lot of weightage both in mains and advanced, and a lot of questions are asked for NEET as well. So whatever exam you are preparing for, electrostatics is something you must not and you should not leave, because it's scoring as well, right? Because all you have to do is apply the laws of the Newton's laws and the concepts of mechanics onto charges. That's all, right? So with that, let us begin a little bit with electrostatics. It is called electrostatics. Why it's statics? Because we're talking about charges which are static. Okay, we're talking about charges which are not moving. Because you have already done this chapter, I guess by now. So you know that after this we learn something called as electric current, which is the study of charges when they're moving, right? So here charges don't move. And so we begin quite simply by the properties of charges. That one of the most important property of a charge is that a charge is quantized, right? That no matter what amount of charge you have, it will always be a multiple of the charge of an electron, right? The magnitude of the charge of an electron, to be precise, right? So it will be just n times E. Then we learned that charge is quantized, and a few more simple properties of charges, right? And then this great guy Coulomb in, I think, 1600s or something, he came up with this formula which gives the force between two charges, that force between two charges is equal to K times Q1 Q2 by R square, right? When Q1 Q2 are the charges and R is the distance between them, you know that. One important thing about this this force formula is that it is applicable only in case of point charges. See, otherwise you will not be able to define that R between the charges, right? And if you have learned the chapter of gravitation, which I'm sure you must have, then you would know that the force between two masses is given by G m1 m2 by R square. And I'm sure that you would have seen a very striking similarity between these two formulae. Except for one fact, which you should remember, that the K which we have in case of electrostatics is equal to 1 by 4 pi epsilon naught times epsilon r, right? Where epsilon naught is called the permittivity of free space or permittivity of vacuum, and epsilon r is the relative permittivity, okay? Whereas G in case of gravitation has a constant value, 6 point something 10 to the power of minus 11, right, in SI units. So what is this interesting thing with the constant in electrostatics is that this constant depends on the medium, okay? So if you're talking about the force between two charges in vacuum, that's going to be different from the force between two charges in the glass medium, all right? In fact, the value of ER for vacuum is 1, and for any other it is more than 1. So the maximum force which you can have is in vacuum. You have learned all those things. So very simple questions can be asked from this. In fact, what they do is usually they combine the questions of mechanics with electrostatics, as I was saying. They would just give you like, I don't know, a string and a bob, and the bob has this much of charge, and it is hanging, and then what angle will it hang to? If I immerse this in this liquid of this particular density, then if the angle changes by this much amount, then what can you tell about its charge? So basically you have to apply the ideas of mechanics, and in this case if you're dipping it inside some kind of a liquid, then some ideas from fluid mechanics, okay? So electrostatics is this extra information which you have, okay, which you apply on top of the things which you already know, okay? So electrostatics is something you should not take very carelessly, because it's really scoring. And once you have done that chapter, all you have to do, is just go through your notes once. You don't have to like prepare it all the time, because every time you're preparing or making questions of fluids or mechanics, you're basically doing electrostatics, right? That's what you're doing. And then, after that we had the idea of electric field, which was also an interesting idea. The word field means, a region around something. But in physics, we just casually use the word electric field, which we mean actually not electric field, but what we mean is electric field intensity, right? Which we define as the force acting on a unit charge at a particular point. So by doing that, what we have done is we have defined a particular value of something at every point in space. That, okay, this point in space, if I keep a unit charge, how much force it is going to feel, that is the field present in this region. Okay, that is the electric field at that point actually. All right. So electric field had very interesting ideas. We had distribution of charges, and because of the distribution of charges, we calculated electric field because of a uniform rod, infinitely long rod, and then because of a ring, and all these different differentiation methods are there. Okay, in which you take a small element, then you integrate all the time through all the length of it. You know the deal, right? We do it all in that way. You know why? Because for that whole distribution, you cannot directly apply Coulomb's law. Why? Because Coulomb's law work only for point charges. So you have to take a small point there, and then you have to integrate, and and integration also you have to be really careful, because electric field is not a scalar. Electric field is a vector quantity. So if something is a vector quantity, while adding it, you have to make sure that all the vectors are in the same direction and all the blah 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 deals are there, right? Then from electric field, the next thing which we learned was this infamous idea of Gauss law, right? Gauss said that if you imagine a surface, okay, some surface, and if you take a very small area element in that surface, which we usually represent by ds, sometimes by dA, and if you find the integral of E dot ds, right, by dot ds is a vector we have made there, a vector, okay, a vector we have defined which is outward, in the outward direction, that is away from the closeness of that shape, okay, outward normal. Then we do E dot ds and we integrate that, and the Gauss says that that will be equal to the charge enclosed by epsilon naught. Okay, that is a fascinating idea. All right, and in case of symmetric distributions, we exploited the idea of Gauss law to find the values of electric field. Right, remember that? So we take symmetric surfaces, so that that integral of E dot ds, we want to get rid of that dot, so we make sure that the electric field and the area vector are either parallel or perpendicular. You remember all those derivations you must have done. Okay, then we make sure that the Gaussian which we have chosen, by the way, the Gaussian surface is also sometimes called Gaussian. Okay, that's just a lingo. So the Gaussian which you have chosen has to be chosen in such a way that the electric field is either 0 or constant, so that you can take that also out of the integration. Okay, and then all you're left with is that integral of ds, which is very simple, right? And that's how we calculate the electric field into different symmetric distributions. Okay. And in case of Gauss law, you get these kind of questions are very famous, where you have, for example, you have like a jug, and just on the center of the jug, you have a charge, and they're asking how much is the flux through the jug. And then you just, if you don't know how to do that, you look at the shape of the jug and you're like, oh my God, this is such a weird shape. How am I going to integrate E dot ds all over that jug? Okay, you don't even, they're not even given the function of that jug. Okay, even if like you go to a real mathematical prodigy, you would take like, I don't know, like days to solve that. Maybe not days, but surely like hours to solve that. Then you realize that, oh, we don't have to do that because Gauss is with us. And Gauss says that if you just close that thing up, so if you've got a beautiful jug and a charge in the center, what you do is you take another symmetrical jug and you complete that surface, you close it, and then you say that through this closed surface, the flux would be Q by epsilon naught. And if the flux is Q by epsilon naught through this closed surface, and you have to find the flux through the half surface, that will just be Q by 2 epsilon naught because of symmetry. Okay, so you exploit this idea of symmetry a lot. Okay, you also have questions where you have a cube, and on the corner of the cube you're given a charge, and they're asking how much is the flux through the sides of the cube. Then what you do is you complete that cube from all sides. You make it a pack of 6 cubes, right? If you have a ball or a point, if you want to completely surround it, you need 6 cubes, right? 6 or 8. You need 8 cubes. I'm sorry. Yeah, you need 8 cubes, because you have learned that in solid state in chemistry, right? That the BCC structure, it needs 8 cubes to completely surround it. So that flux get divided into 8 equal parts because it is symmetric and all that we have learned. So that was a really interesting thing in electric field. Then we got around the idea that this electrostatic force and electric field hence is a conservative field. You know what a conservative field is? The definition, of course, we did in work power energy, where the idea was that if the net work done on a charge in a closed loop, or any charge or any object in a closed loop by a field is 0, then it is a conservative field. And conservative field, the interesting thing about conservative fields was, that conservative fields do not depend on the path of which you've taken. Okay, so for example, you are moving a charge from A to B. You go this way, you go that way, you go any way. If you're going in an electrostatic field, the amount of work done by you would be the same. Okay, and whenever fields are conservative, you can define a thing called as electric potential. Okay, this is a common misconception which students usually have, that electric potential is something which is absolute. But electric potential and also electric potential energy is something which is defined between 2 points. It is the work done, in case of electrostatic potential, it is the work done in moving a unit positive charge from one point to another point. Okay, that is defined as the electrostatic potential. Unit charge. Okay, so let's say you're taking 10 coulomb charge, whatever work you do, let's say you did 10 joules of work, you just divide that by 10. Okay, so you get 1 joule, 1 joule per coulomb. That is, joule per coulomb has a different name, we call it volts, right? So that much volts of potential difference is between these 2 points. Okay, so one interesting thing to remember here is that whenever you have an electric field and you're moving a charge around in that electric field, and whenever you're going against the electric field, of course, from the agent side, you'll have to do work, so the potential increases, which very much similar to gravity. Say the gravity is always acting downwards, right? But if you have a mass and if you're taking that mass upwards, then you know that the potential increases. Why? Because you're moving it against the field. But if you're moving it in the direction of the field, then the potential decreases. The same thing is true with electrostatics as well. If you're moving a charge against the field, the potential increases. If you're moving a charge towards the field, the potential decreases. Okay, and this is actually the reverse when you have a negative charge. Okay, that is one thing you have to be careful about, because in gravitation you don't have negative masses, but in electrostatics you do have negative charges, right? So be careful about that negative. So sometimes I've seen that a couple of times in mains also they have tried to confuse the students by this negative sign thing. So be very careful and cautious, because I feel that electrostatics are just free marks. If you know mechanics and fluids, don't lose your marks on these silly things. All right. So that's what we learned: electrostatics and electrostatic potential, and then we saw electrostatic potential energy, which is also a very fascinating idea, right? So one very interesting thing in that was how much is the electrostatic potential energy of the system. Okay, this is one thing which they usually ask, like a system of 3 charges which are placed in an equilateral triangle or something. Okay, so there the idea was that the amount of electrostatic potential energy which this system contains is equal to the amount of work done in making the system. Okay, so you start making the system. How would you make the system? You bring first charge, and that the interesting thing about the first charge is you do no work against anything because there is no field present. So the first charge comes for free. Okay, and then you bring the second charge, and for that you do work against the electrostatic field of the first charge. Then you bring the third charge, and for that you do the work against the electrostatic field of the first and the second charge. Okay, and that's how we find the total electrostatic potential energy. In fact, you don't actually have to do all this. In the end, if you remember, we came to a formula where if you have 3 charges, okay, the electrostatic potential energy will be kq1 q2 by r12 plus kq2 q3 by r23 plus kq2 q3 by r23, okay, and 3 1 like that. So let's say you have 3 charges. For every pair you get a term. Okay, for a q1 q2 pair you have kq1 q2 by r12. For 2 or 3 pair you have kq2 q3 by r23. Like that, for every pair of charge you get a term. Okay, so let's say you have 4 charges. How many terms will you have? For every pair, if you're getting 1 term, then you have learned in mathematics you have something called as combinations, right? Which tells that the number of ways of selecting 2 things out of n things is nc2. Okay, so if you have 4 charges, so 4c2 terms can be made. 4C2 is equal to how much? 4 into 3 by 2, that is 6. So 6 terms will be there. So 6 pairs can be made, and if we just add beautifully all those pairs, you'd get the total electrostatic potential energy in that case. Okay. So if I move ahead in this chapter, after that we learned about conductors, which is also a very fairly easy idea, right? You put any amount of charge on a conductor. See, there's a lot of theory around it, but in the end you have to take away some final thing. The final thing is, if you put charges on a conductor, the charges are going to go on the surface. Okay, because one reason is charges are free to move around it, so they will always repel each other. If they repel each other, they will try to be as far from each other as possible, right? And the other line of reasoning which is given is that if you take a Gaussian surface inside the conductor, inside the metal, says that the surface itself lies inside the material of the conductor, right? Then you know that the electric field inside the conductor has to be zero. That's also underlying fact. The electric field inside a conductor under electrostatic conditions is always zero. Okay, so if electric field is zero, then the flux is going to be zero. And if flux is going to be zero, then Gauss says, charge enclosed has got to be zero. So if charge enclosed is zero, then you cannot have any charge, any net charge inside that Gaussian surface which you have chosen through the material of the conductor. It means that all the charges will reside on the surface of that conductor. Okay. Another interesting thing in conductors in this chapter was that the electric field which comes out of conductor always comes out perpendicular to the conductor, which makes the conductor an equipotential surface. Okay. By the way, we didn't speak about electric equipotential surface. That's also a very interesting point. Is a very interesting concept from where they like to ask questions. It's a surface, okay, where all the points are at the same potential. Okay, what does that mean? It means that if you move a charge from one point to another point within that surface, you're not doing any work. Okay, although electric field is present. Well, if you're not doing any work and electrostatic field is present, then shouldn't that mean that you are moving that charge perpendicular to that field? Yes, and that's why always equipotential surfaces are surfaces which are perpendicular to the electric field. Okay, that is one very interesting thing. So sometimes they give you questions of, they have given the electric field and they have to draw the equipotential surface. So if you draw the equipotential surface, then you know that equipotential surface has to be perpendicular to those field lines. Okay, field lines is also something we had seen. I think I skipped that, but briefly if I discussed, then you know that wherever we represent the electric field by electric field lines. Wherever the lines are thick, we know that the electric field is more. Wherever they're rare and they're far apart, we know that the electric field there is less. And a tangent to those fields gives you the direction of the electric field. Okay, and I don't know. I think by the time of Coulomb, I don't think Coulomb came up with electric field lines idea. I think Faraday was the guy who came up with the idea of electric field lines. I think from his time, people are asking this question: why don't two electric field lines intersect each other? Okay, because the tangent to an electric field line gives you electric field. No, actually it gives you the net electric field at that point. So if two electric field lines are intersecting, at that point if I ask you to make a tangent, you'd be like, oh, should I make tangent to this line or should I make tangent to this line? Okay, two different people will make two different tangents, so you can have more than one tangent there. It means that there are two directions of the net electric field. That's not possible, and for that reason electric fields do not intersect. Okay, they just merge with each other. All right, so that was the whole chapter more or less covered. And then see, there are small concepts like let's say a charge is moving and it goes from some potential Vi to a potential of Vf. Then the work done is the Q times Vf minus Vi, which is the final potential minus the initial potential. And I also told you that potential is always a relative quantity which is always defined between 2 points, work done in moving the unit charge from one point to another point. What we do is the first point we always take it at infinity and we define the potential at that point to be 0. Okay, so sometimes they ask you a question, because of a unit charge, what is the potential at a certain point? Okay, so you remember the formula, right, which is also something we learned, which is kq square by r, right? So I'm sorry, not kq square, it is kq by r. So kq by r is the formula for the potential, right? But when you say that is the potential of that charge at that point, it means that it is the potential with respect to some other point. In this case, it is with respect to infinity. The potential at infinity is considered to be zero. Okay, that is like a assumption which sometimes they forget to mention, but they should not, because it kind of confuses students and I don't like it. So that is the thing, that with potential you have to be careful. See, sometimes they give a question that, you know, the potential at a certain point was 5 coulombs. Okay, and this was when the potential at infinity was 0. Now all of a sudden the potential at infinity is increased by 3 coulombs, volts, sorry. Potential was 5 volts, and suddenly at infinity the potential is increased by 3 volts. What will happen to the potential at the original point? It will also get increased by 3, so it will become 8 volts. Okay, because the difference between infinity and this point has got to be 5. That is the whole idea. So that is the chapter of electrostatics in brief. Okay, about charges and everything. Sometimes I found some students get really scared with all these charges, and students who are like were good in mechanics. So you know, it's fairly simple. The concept of potential is also something you've learned already in the chapter of gravitation, all right, and mechanics problems, like, you know, as I told you, a bob hanging with a string, that kind of a problem are asked. And this is also a very commonly asked question in electrostatics, where you have a charge moving, let's say a helium nuclei moving towards a heavy nucleus of this atomic number. Then what would be the distance of minimum approach? Okay, it was sent with this speed. So in this kind of a case, you can apply the conservation of energy. You can say that initially they were very far apart, so the potential energy which they had was almost 0, because this is also something we learned, that between two charges the potential energy is given by kq1 q2 by r, right? So if they're very far, the potential energy is almost 0 because r is tending to infinity. So, but it has a kinetic energy, and that kinetic energy must be equal to the final potential energy when they are very close. So these kind of problems are asked in electrostatics, and almost like I haven't seen, I think I've never seen a paper of physics in this country where there is no question of electrostatics. All right. There's also the idea of dipole, which is also very decently asked idea. Dipole is nothing but, dipole is like this pen, you know, you have a positive charge, you have a negative charge, that's all. It's like an arrow, we represented by an arrow. So if you have an electric field, what happens if it is kept like this, then the force on this part is acting this way, this part is acting in that way, because you have a negative charge there, so it gets inclined like that. Okay, so they ask questions on the torque acting on a dipole, which is I think P cross E, right? The P is the dipole moment, and because this is a very brief summary, so you know the dipole moment, right? Q times the distance between the two charges, that is the dipole moment. And P is a vector which is defined in the direction from the negative to the positive charge, which is opposite, by the way, in as to in the case of chemistry, because in chemistry you have dipole defined from positive to negative. So that is what dipole is, and that is the torque in the dipole, is at P into P cross E, and the potential energy of the dipole is given by minus P dot E. Okay, and you know that this is positive, this is negative, then this is the stable equilibrium for the dipole, because when you shift it this way, the dipole comes back like that. If you shift it that way, the dipole comes back like that. So dipole can oscillate this way. Okay, and at this point is when we consider the energy to be 0. Okay, and this point the energy is maximum. Okay, the energy is maximum at this point, and because the potential energy is maximum at this point, this is an unstable equilibrium. That is, if you displace the dipole a little bit, it's not going to come back. The dipole is going to go this way. Okay, I hope you remember the idea of stable, unstable, and neutral equilibrium, right? Stable equilibrium is one where our object is in equilibrium, and if you displace the object a little bit, then it comes back to the original. It tries to come back to the original point of equilibrium, like it oscillates. The best example is a marble kept on an open bowl. So you have a marble and you displace the marble a little bit, the marble will try to come back. So that's the case of stable equilibrium. The unstable equilibrium case would be, the best example is a marble kept on an inverted bowl. It is in equilibrium because it is kept precisely there. You have a bowl and you have a marble on top of it. But if you displace it a little bit, instead of the tendency of coming back to the equilibrium position, it has a tendency to go away from the equilibrium position. Unstable equilibrium. And the best example of a neutral equilibrium is the same marble kept on a floor which has some friction. So it is in equilibrium. When you displace it, it is still in equilibrium. It doesn't have a tendency to come back or to run away. Okay, so that is neutral equilibrium. So this was the chapter of electrostatics in brief, and I think we'll take up Darshan Vaishnav has asked a question that tangents at various points at contact meet together when its angle is. Okay, I don't understand. Tangents at various points at contact meet together when its angle is. I don't think that's a complete question, Darshan. I think you should repost your question. I'll try to answer that. Okay, Deepak is trying to ask, can we calculate the field due to Avogadro number of course you can calculate the field due to Avogadro number of electrons. Okay, Avogadro number is what, 6.023 × 10 to the power of 23. That many electrons. Okay, and each electron carrying a charge of 1.6 × 10 to the power of -19. You multiply both the numbers. That is the total amount of charge you have. Now you want to find field, Deepak. Okay, so Deepak, you should know that whenever you're talking about field, you have to specify how far from those electrons you're talking about. If you're talking about at a distance r from those electrons, then you can just find k, your constant of electrostatic constant, the value of which is 9 × 10 to the power of 9, multiplied by the charge, which will be Avogadro number times the charge of an electron, divided by r square. Okay, that will give you the electric field. That's very simple. So Ayush is asking a question, Ayush Dash, how to solve the problems on mechanics and electrostatics. Oh, see, this is a very generic question. How to solve the problems in mechanics? See, my suggestion to you is there is something called as rational intuition. Rational intuition is something which gets developed when you do something rigorously again and again. Okay, so you learn the concepts of mechanics, but by learning, by attending the class, don't ever think that you have gotten how to do it, even when you have understood the concept, because only when you start solving more and more problems, you'd realize that, oh my god, I had not understood this clearly, you know. Okay, so these are the 4 steps which are important in whenever friction comes into the picture. These are the steps involved in drawing FBDs. Okay, and in electrostatics, these are things I have to be careful about. Okay, this comes to you automatically. It comes. You don't have to push. It will come automatically to you only when you solve a lot of problems and actively engage in that chapter. Okay, learn it with interest. Okay, all right. So we have a question from Shrikar Reddy, and he says how to solve problems regarding point dipole. First of all, I have never heard anything called point dipole, but I think you mean the dipole which I was talking about, where you have 2 point charges. Okay, plus q and minus q. How do you solve problems? See, it's a very simple thing. It's just an arrow. Okay, which behaves in such a way that it always wants to get inclined in the direction of electric field. Okay, the questions which are asked are see, one thing, if you want, I can tell you. For example, this is a dipole. This is the positive side, negative side. Okay, they ask you a question of what is the electric field on the axis of the dipole. So this line which crosses through this dipole is the axis of the dipole. So any point on this axis, the field is given by P upon, not P, 2P upon 4 pi epsilon naught R cube. Okay, R cube. Sometimes people wonder, in case of dipole, the field is varying with the inverse of the cube of distance. Okay, doesn't this defy the Coulomb's law? But that's not so, because we arrived at this formula using Coulomb's law, and because we have made an approximation that the dipole is really, really small, so that's why we got that R cube. Otherwise it would have been R square plus something. Okay, so the electric field, there is 2 times of P upon 4 pi epsilon naught R cube. On the equator, the electric field is P upon 4 pi epsilon naught of R cube. And if you want to find electric field at any specific point, for example at an angle theta, then I'll tell you one trick. This will be helpful. What you do is you exploit the fact that the dipole is a vector, and what you do is you resolve the vector along that line and perpendicular to that line. Now what happens, because the P cos theta, that is the component of that dipole along that line, right, would produce how much electric field there? 2P cos theta, because that is the value, upon 4 pi epsilon naught R cube. R cube is the distance between that point and this point. Okay, and because of that equilateral, you have P sin theta upon 4 pi epsilon naught r cube. So that's how you can solve problems of dipoles. I think you should solve some more examples so you'll get that. Okay, so I have a question from Ashwin Gowda. Can you explain off-force principle? I have never heard of off-force principle in electrostatics, but well, I will leave a comment in case I find something on off-force principle. It's a very strange name. Okay, so Deepak is asking, even though charges are quantized, Gauss law treats charge as bulk of electrons. Why? Well, charges are quantized. Why? The question is, why should Gauss law treat charges as quantized? So charge. What is Gauss saying? Gauss saying is, so what are you trying to say, Deepak? You're trying to say that Gauss should have said that instead of saying the charge enclosed inside a Gaussian is Q epsilon naught, Q enclosed by epsilon naught, you should have said it is n times of number of electrons or protons enclosed divided by epsilon naught. That's what you should have said. But everybody knew that they are quantized, so it means the same thing. Okay, it doesn't. So even when you treat it as bulk, you know intrinsically that we're treating it as bulk, but it is not bulk. Okay, so saying it whether completely Q enclosed or n into E doesn't make any difference in your calculation. Okay, so that's why Gauss, I think, being very prodigal, mathematical genius, Gauss never, I think, thought of all those. So I think a couple of more questions we can take, and Amruta Manjusha is asking a question. Okay, your question is, what's the best way to revise all topics before exam? Okay, this is a good question. This will be helpful to everyone. Now, what is the best thing to revise all the topics before exam? See, first thing is, one thing you must have already realized, that this JEE thing and this competitive exams throws in a lot of knowledge to you. Okay, and if you're not doing proper knowledge management, that if you're not making proper, see, I find a lot of students who don't make proper notes, you're going to suffer. Okay, not because you're not smart, because there's a lot of information. Okay, make proper notes, and every once in a month you go back and revise the things which you had already learned. See, I used to do one thing, and I want to suggest everyone to do that. That's the best thing which worked for me. It might not work for you, but try it. Every day, whatever you learn, you just take a diary and note that thing down. Today I learned this, today's date. Make some doodles and make it more interesting. Oh, this I learned, this joke, sir told this joke, or this is this thing my friend made. So what happens a month later, you're just flipping through your diary, it's like, oh yeah, I learned that concept, man. I learned that 1 month back. I don't remember it. You just go and just, oh yeah, that's what it is. Yeah, now I remember. See, your mind works in a way that if you don't revise, the ideas are going to just, they're going to get dusty, and you might know how to do it, but you don't have that much time in the examination. You have just like 3-4 minutes to solve a problem. You cannot just sit and like, oh, how did it go? Okay, so the charge was like that and the conductor was like that. You don't have that much time. So there's this very famous book. Read it when you get to a college or some place by Daniel Kahneman called Thinking Fast and Slow, where he talks about 2 modes in which your mind works, system 1 and system 2. Okay, so what I think is that you need to practice questions so much that most of these concepts start coming from your system 2, which is system 2 is, by the way, for example, you ask me a question, right? If I can't immediately answer it, what I'm doing, I'm thinking, okay, yeah, and then I'll be able to answer it. That doesn't mean that I didn't know it. It was there in the back of my head, but I had to pull it through. Okay, but if you ask me 3 plus 3 is how much, I was like 6. What is the integration of x squared? Like x cubed by 3 plus c. It's just there in my system 1. And if it is in my system 1, because I've repeated it so many times. Okay, so you have to solve lots of problem to get that. And just before the exam, as you asked, what is the best way to revise, is to make short notes. Okay, you read the chapter, you make your notes, and then you try to not use more than like 1 sheet of paper. And in that 1 sheet of paper, you write down all the formulas and all the important points which you have to learn, and just you make a file out of it. Okay, and before exam, you just go through that file. And in fact, I would suggest all of you to make a separate notebook for every chapter, so that all the problems which you're solving is solved in that same book, in that same notebook. All right. So I hope, Amrita, you're satisfied with that. And so I'll take one last question. See, we have worked really hard on this our app of BYJU'S app. We have very interesting videos. We are using animation and everything to make the chapter, to give you a real feel of the subject. Okay, so the Van de Graaff generator and the Gauss Law and everything it's been explored. So I think if you take some time out, download our app, and it's free for 15 days. And just explore through it. There are lots of videos, not just on physics and electrostatics. You just get videos on chemistry, you have videos on mathematics, you have these interesting videos coming up, how to prepare for examinations and all that. So I think you'll find it interesting. And also on YouTube, we have got a lot of videos we keep updating. So please subscribe to our YouTube channel and watch those videos. We work to make everything as clear as possible, all right? I'll take a last question. Srikar Reddy is asking, sir, point dipole means that, you're explaining, okay, point dipole means that I want to say when the distance between the charges become infinitely small. Oh, Srikar, you asked this question which falls out of the realm of 11th and 12th, because see, what happens is when the distances become very, very close, I don't know if I should tell this, but let me tell you that the physics which you are learning right now in 11th and 12th, that physics is not completely valid in there. You get into a new kind of physics that is called quantum mechanics, and I know you must be hearing this word all the time. But when distances become very small and with microscopic particles, you enter the realm of quantum mechanics, and there these classical concepts which you are learning, they just don't work. Okay, why they don't work? It's also a very profound question, and I don't think we have enough time to answer that, although I would like to discuss on it sometime. But it so happens in nature that it doesn't work, and we have a different kind of formulation which you learn if you go to an engineering college, or you can learn on your own, because there are a lot of YouTube videos also on that. So Gulshan Kumar says that if you put 1 coulomb charge at the center of a clock, radius of the clock is 1 meter, okay, and 1 to 12 R represent 1 to 12 coulombs, then what is the net force on the central charge 1 coulomb? See, this is a very easy question. Okay, what is there in this question? The 1 coulomb charge is on the center, 1 coulomb charge is there on the top. So at 12 o'clock you have 12 coulombs of charge. As you're saying, every hour, for example, at 1 o'clock you have 1 coulomb charge, 2 o'clock you have 2 coulomb charge, 3 o'clock you have 3 coulomb charge, like that you have charges all around. You just find the force, because the 12 coulomb charge will be applying a force of K into 12 coulombs into 1 coulomb divided by the distance, that is that R square, and the 6 coulomb from below will be applying a force in the opposite direction, so there will be a net force in the upward direction of 6 coulombs. Like that, the pairs and pairs, you can just you can find the net forces, and you can just do a vector sum of that. It's not very difficult. All right. So I hope you enjoyed the session, and you got to learn something which you didn't know. And keep coming back to our FB live sessions and keep asking interesting questions, and we're here to help you out all the time. And download our app, all right, and check out the videos which we make. They are pretty darn interesting.